And I'm here with,
Yeah, I'm Mike, and
yeah, we're working on a webcam-based ADHD screen tooling using eye tracking and behavioral tests. Yeah. So to start, we want to establish kind of like our table of contents, what we're going to go over today. So first, we're going to introduce ADHD, kind of provide a definition for those unfamiliar with it. Next, we're going to talk about the accessibility of screening with ADHD and why we created our research, why we did our research and why we created our project. And three, we are going to talk about the technology used behind that. Mike will cover that. And then we'll address challenges and solutions that we faced while researching eye tracking with ADHD. And finally, for the last two, we're going to cover kind of our experiment and our results, what we have done with testing currently. And finally, we're just going to talk about future research. Yeah. So to start off, I'm going to do a brief introduction about ADHD for those who don't really have a deep understanding of what it is. So first of all, what ADHD is, it stands for attention deficit hyperactivity disorder. And this is a neurodevelopmental disorder. So it comes from either from birth most of the time. And kind of the prevalence of ADHD based on what we searched in the CDC this year, as you've seen on the slides, almost in children, it's almost roughly 10 or almost nearing 11% of children. So almost 1 in 10 or more. And have been diagnosed. So that leaves a lot of room for many who haven't been diagnosed. And kind of the number is 6.5 million based on the current population of the United States. And same thing with adults. Adults, it's 6% of the adult population, and that would be 15.5 million US adults. So it is a widespread kind of diagnosis. So yeah, so with ADHD, the key symptoms of those with ADHD are first inattention, hyperactivity, and impulsivity. So a few examples of these in different settings, I'd say are inattention at school. It could be seen as maybe they're struggling to complete assignments on time, or they miss details, or a lot of work is either late or incomplete. And this is a struggle that people with ADHD often face. And with hyperactivity, an example at work is maybe in meetings, people might appear restless. They might fidget with their arms, hands, or they might move around a lot in their chairs. And this can be because they're distracted, and it also maybe could be distracting to other people. And finally, impulsivity is the third category. And at home, this could result in kind of quick decision making. People maybe buying something online at one time, then thinking again, if they thought longer, they wouldn't have bought it. So it is a prevalent issue. So with these symptoms and kind of the prevalence of ADHD, it's important for people to get ADHD screening. And ADHD screening helps kind of the 2 points I laid out on the slides are treatment planning as well as people with education. So treatment planning, these can be through either medication, social skills training, or behavioral therapy. And these are very important as they help as an early diagnosis helps manage the disorder effectively and not cause it to develop harmful habits that might limit someone's potential in the future. And on the terms of education, because as we saw 10%, 10.47% actually of children. So with education, it can help provide through individual education programs, kind of extended times, accommodations, as well as maybe teachers providing organizational skills to help the students. Yeah. So now moving on to my second topic of the importance of accessible screening. So with accessible screening, so the current problems with accessible screening, I'd say are three: high cost, limited access to professionals, and three, it is very time consuming. So as a basis of right now, based on the CDC, a basic evaluation of ADHD is between $500 to $2,500. And a comprehensive, more deep analysis of someone's ADHD disorder is from $1,000 to even $5,000. So this is extremely expensive, and many in the low income or rural and underserved areas may not even have the chance to even afford this treatment, or even a diagnosis, not even talking about the treatment at all. And second, like I said, limited to access of professionals, because currently many screening methods, they take in-person visits, which causes people to have to find professionals in the area. And if there aren't many professionals in the area, they may have to travel far away or travel
many hours. And finally, kind of the standard tests of ADHD, they take several hours and several in-person treatment sessions. And it's also like very inconvenient if someone is a student or they have to drive far away, even to just take the test. So like that's why with our project, we're exploring eye tracking technology with ADHD, because we saw like the benefits of researching eye tracking being first cost effective. We can make this program, we want to make this program like free testing so that we can incorporate all those like unobserved or like rural area people. And second, it's accessible anywhere. Eye tracking, you only need a device that has access to the internet and also just a device with a camera. So it's very easy instead of going to an in-person, traveling hours and spending lots of money. And third, it's efficient. With our test we were able to develop, it takes roughly 20 minutes per versus like a few hours that the standard would take. Yeah. So now Mike's gonna go and cover like kind of like the technology or like methodology that we have been like we use to start our research and create our project.
Okay, yeah, I'm Mike. Yeah, I'm gonna talk about some of the technology. Yeah. So language, we use multiple languages, and for the backend, we use Python, which powered our web applications and helped manage data through like processing tasks. And we also used Flask, which is a micro web framework for its simplicity and flexibility. And where it was implemented, yeah, it was in like files. And it's used to like handle HTTP requests for a website and to load data and manage questions like questions for a test or like other parts of like our screening part tests. And we used it because it's pretty easy to write and maintain. And Flask is really like lightweight, is a really good solution for building up applications and without the need for like a complex setup. And for the front end, we use JavaScript, and this is like handle user interactions and control the webcam for eye tracking and process real-time data. And like the library we used was called WebGazer. We didn't make the eye tracking ourselves because it's extremely complicated, and we downloaded that from online. And JavaScript is really useful because it runs in the browser and it provides the ability to handle real-time events, such as the eye tracking, and it is essential for creating interactive and dynamic web pages. And we also used HTML, which creates like the structure for web pages. So we have like different sections of the website you can go to, and it helps store our data like locally, and it's really like how we structure our entire website. And another language we used was CSS. This was mostly like for styling and design. And it helped us just have more visual like depth for our web pages and design it so it looks more appealing and functional. And for the tools that we used, yeah, we used WebGazer, which was a JavaScript application, and it was made online by, I think it was a college, and it helps track a user just using their webcam without any other additional technology. And yeah, like you can use it right in the browser, which makes it like really helpful for newer gaze instead of like having to pay anything else for extra like hardware. And another library used was Flask. This was mostly for our Python coding, and it helps us like really easily create like this application and manage routes and render HTML templates and serve like the content. Yeah. And another library we used was JSON. This was mostly for like storing and exchanging data so that the user can we can have like the user's data for the testing. And like, for example, like we had some questions like a survey, and that's like where it was used like to save and store answers for that testing. Yeah. And whatever APIs we used was RESTful AI. It's for defining routes and like handling requests. For example, like a different URL could map to like different functions in the app and could serve content and handle logic. And then for the storage, we use a lot of like local storage based on like your own browser. And it allows the system to improve accuracy over time without like requiring like the user to continuously like calibrate like their eye tracking. And it stores users' data so they don't have to like wait online for like for the the results to come back from a external website.
Okay. Yeah, so now we're gonna move on to kind of some challenges and like how we face those challenges while we were like designing where we were conducting our research. Yeah. So with challenges, we bullet pointed these in red on this slide. So kind of the three main topics were accessibility, kind of the eye tracking accuracy, which was our main, I'd say, main challenge, and third, choosing which tests to do, because ADHD tests they traditionally take many hours, so we had to find a way to find the most efficient test to encompass it in the shortest amount of time, us being 20 minutes. Yeah, so with accessibility, we had an issue, or like we were talking about like kind of online traction. Because like online traction, there's a lot of maybe other websites that would cost money. So kind of promoting this up, but also kind of maybe paid versus open access. And we decided to use a free and public service, and kind of talking more about our eye tracking accuracy. So while we were experimenting with the calibration accuracy, because we're using eye tracking, this calibration was the most kind of impactful part of it, as it's kind of the basis for the diagnosis that the person taking it would receive. And a lot of times at the start, the calibration would have to take 3, 4, 5, or even maybe 6 times per calibration. So after many tests, we set it at a 75% calibration success minimum. That's what we found most successful, while also not taking too much of the user's time. And third, we had each calibration after each test. So this allowed for the system to be as accurate as possible, so that kind of the person's results and tests are also like accurate as a result. So now on like the next 3 slides, Mike will be going into more depth about kind of which tests we chose and kind of how each test measures different things.
Yeah. So our first test we chose was like visual attention test. This would have 10 a user, it would show a user 10 random images. And at the start, it would pick one of those images that the user wouldn't have to press like the space bar when they see. And we took these images from Unsplash API, which is like a free library of I think thousands of photos. And we did it this way so that's like not as boring as just like a regular test. And also just only 10 images so that it doesn't take as much time. And the reason we designed this was to track the user's eyes and see if like they're staying focused while they focus on the images. And our second test was called continuous inhibition. Like this was an actual test that like doctors have used, and it will have it'll display random letters to a user, and it'll ask them to like press space as quickly as possible, except when they see X. So this helps them with like a user's sustained and selective attention, and it will like test impulse control by tracking errors when a user like incorrectly reacts or fails to like react to stimuli such as like the X, and accessing the ability to inhibit responses. Yeah. And our third test was called an interference test, which has these are like pick a reading difficulty at the start, based on like other children, teen or adults, so that like they can actually understand the passage. And then they'll be reading like a passage as shown in like in the images, while at the same time like images from Unsplash API will be like displayed in the background and like popping up in an attempt to like distract the reader. So like this will measure like how well like a user can handle conflicting information and distractions, and like test their ability to prioritize information and like important stimuli over like irrelevant stimuli.
Yeah. So now we'll talk about kind of the results page that we designed that we will get from all 3 of these tests. As you see on like the right, starting off, in each 3 section, you can see the 3 tests: visual attention number 1, continuous inhibition number 2, and interference number 3, all of which Mike just explained. So kind of going into more depth on what the results screen kind of displays and what we're looking for when we were testing users. So number 1, covering kind of average reaction time. So this tracks kind of the time between stimuli of the presentation and the user's response. So for example, kind of like the X, pressing that, we're measuring the time between each time they press X when they don't press X. And it kind of indicates to us like the processing speed and like attention capacity of like the person. Number two, kind of the reaction time, like variability, and this is tracked by kind of the consistency of the person's reactions across multiple trials. So all three of these trials are all doing that, and it's tracking kind of the person's consistency of reactions, like I said, and it kind of reflects lapses in attention or inattentiveness. And we don't only just track it on one test because we want to make it as kind of accurate as possible. Tracking it over 3 tests makes it more accurate than just basing it off just one. Again, now with kind of omission errors, how it's tracked is we like record the relay time to response to a required stimuli. And also it kind of like shows, again, it's another test for like attention and inattentiveness, and it's like a high rate of indicating person maintaining focus. So this test is more measured in the like interference test. When the image pops up on the screen, it'll measure if the person's eye like goes there and the amount of time it'll take to go there. And finally, measures of error. This is measuring the commission's error, and how it's tracked is it's recording when the user like incorrectly responds to a non-target stimulus. So this non-target stimulus could be another when pressing the space bar on another letter other than X. For example, if they pressed A, when an A showed up and they pressed the space bar, it would track that down, and it indicates impulsivity, which is one of the metrics that I stated before as kind of one of the main defining characteristics of ADHD, and kind of difficulty controlling someone's like actions. And more describing on like the results page on the right. So as you see on the right, there's the target, which is the center dot that we're aiming for. And all of like the other line patterns are the web gazer in our program tracking the user's eye as they are doing this test. And this test can be given to, will display a result of ADHD positive or ADHD negative when given to like a specialist or a doctor, so that they can perform more further tests if needed. And this goes for all 3 of our tests. Yeah, so now moving on, we're going to talk about like the experiment that we conducted in testing the kind of like the accuracy of NeuroGaze and kind of like the results we attained from this test. So in our experiment, like we tested NeuroGaze by dividing participants into a control group and an experimental group. This included children, which are aged from 0 under 12 years old, a teen group, which is from 12 years old to 18 years old, and an adult group, which is above 18. And what we collected data on were 6 individuals with ADHD and 6 individuals without ADHD. And this was already determined by proper diagnosis. So we just wanted to test our accuracy of our results to see if they match up and see how accurate they are compared to traditionally experimented people with ADHD or people without ADHD. And see on the table, this is what we got from our results. So we tested 4 children, we tested 4 teens and 4 adults. And what we saw was the intended diagnosis, 6, and what the diagnosis we got from NeuroGaze. And for a more kind of like detailed version on this page, it's split into pie charts and bar charts. So as you see on the top left, results of testing 6 ADHD individuals on NeuroGaze. So the incorrect diagnosis was 16.7%, and correct diagnosis was 83.3%. And results of testing 6 non-ADHD individuals on NeuroGaze was 33.3% and 66.7%. So just from those two, it shows how NeuroGaze is much better at kind of diagnosing people who have ADHD versus those who do not have ADHD, and it has a larger percentage of giving kind of a false positive for those without ADHD. And we saw from our testing that it's most prominent in the adolescents, so teen groups actually. So with children, it's children group actually, my bad. Children group, almost equal incorrect diagnosis and correct diagnosis, versus adults, they were all correct diagnosis, and adolescents with just teens or 1 correct diagnosis. And we think this is from maybe like children's natural behavior to kind of act kind of more erratic than more mature like teens or adults. Yeah, and again, stating like analysis of our results, 5 out of 6 were correctly diagnosed for ADHD, 4 out of 6 were correctly diagnosed with non-ADHD, and doing the average, the overall is 75% accuracy. And false positives were another problem, which I stated. And so 2 non-ADHD children were incorrectly diagnosed as having ADHD, and this is one problem that we would want to work on. And the system might be, like I said, oversensitive to children, or maybe difficult differentiating ADHD behaviors in younger participants. So kind of, like I said before, the erratic behavior of children. And we think the potential causes are from sensitivity of the algorithm or like behavioral variability, which is like the erratic behavior of younger children. Yeah. So now we're just gonna cover like our future work, what we want to work on in the future. So kind of 2 parts for improvement that we would like to work on in the future are, first of all, improving calibration and accuracy. Because like I said before, we set our minimum bar of calibration to 75%. We are hoping in the future to set it more to like maybe towards the 90s or high 80s starting, and then later high 90s to get as accurate as results possible, and therefore to limit kind of the false positives. And we think we can do this by redefining the eye tracking technology to improve the calibration process and increase diagnostic accuracy, especially for younger participants who showed high false positive rates. Another way I think we could also improve on is not having a calibration after each test, because this does increase the testing time, and which could be more uncomfortable for those with ADHD as they're like impulsive and it's hard for them to stay still. So we're hoping this improvement could just have us just do 1 test at the beginning as just a calibration and it being as accurate as possible. And just the second section, we're thinking of future improvement and research is expanding testing and validation. So kind of expanding testing to a larger sample size and more diverse sample size. We want to improve, maybe we can try with elderly, as well as we want to do more with children, because that is our kind of our target group, because with children, the earlier the diagnosis, the easier the treatment, and kind of the better the treatment is, as it doesn't impact them lifelong and they do not develop kind of very harmful like habits to themselves. So I think we can conduct more tests beyond our just 6 with pre-diagnosed ADHD and 6 without pre-diagnosed ADHD. We can expand it much larger to have more accurate data. And additionally, kind of this can help validate like NearGaze's effectiveness across different groups and demographics, ensuring the tool works accurately for a wide range of users. So we can do it maybe based on like low income, or maybe we can test it on race, but also age. But I think our target is just getting a more larger experimental size and experimental group size. Yeah. So that kind of concludes our presentation about our experiments with eye tracking.